Okay, let's unpack this Earth's history, right? It's not just some dusty timeline. Back in 1868, Thomas Henry Huxley had this incredible way of looking at a simple piece of chalk.
Oh yeah, the Huxley analogy. It's brilliant.
He said that if you truly understood the history held within that chalk, you'd grasp more about the universe than someone learned in everything else but nature's records. Pretty profound, huh?
It really is. And what's fascinating here is that Huxley's ordinary piece of chalk, it's made of fossilized microscopic marine shells, even some ancient crustacean bits. It just speaks volumes about a vastly different Earth.
From the Cretaceous period, wasn't it?
Exactly. Cretaceous, named after Creta, the Latin for chalk. Those same chalk beds, they form the iconic white cliffs of Dover.
Wow.
And geologists back then, and certainly now, recognize that these rocks held fossils of creatures completely unlike anything in our oceans today. It's a tangible clue, like you said, that our planet has this deep transformative biography written in stone.
Absolutely. And that's precisely the journey we're embarking on today, a deep dive into the geologic biography of our planet, drawing from Earth, Portrait of a Planet.
Yeah, not a dry textbook summary.
Definitely not. We're talking billions of years, from Earth's violent birth right up to the dawn of humanity, uncovering some truly surprising twists and turns in this incredible story.
And connecting this to the bigger picture, understanding Earth's history is like piecing together this enormous puzzle using all sorts of clues. Geologists aren't just pulling dates out of thin air,
Yes, we're like detectives.
Totally. Meticulous detectives examining remnants of ancient mountain ranges, we call them origins. Even long after the peaks have eroded away, these events leave telltale signs, like intensely deformed, metamorphosed rocks.
So the rocks themselves change.
Profoundly. And we can use radiometric dating analyzing the decay of radioactive isotopes within these rocks to figure out precisely when those mountains rose.
Okay, so it's not just about scenic views anymore. It's about the intense pressure and heat changing the very fabric of the rocks.
Exactly. And these mountains, as they inevitably erode, they shed just vast amounts of sediment into nearby basins.
Like filling in the low ground around them.
Precisely. Think of it like a raised area slowly crumbling. And these basins, well, they become sedimentary archives themselves, layer upon layer preserving clues about past environments.
And then there's the growth of continents. It's not like all the land we see today just appeared at once, right?
Not at all. By carefully dating different crustal regions and analyzing the rock types, did they come from volcanic island arcs or deep mantle plumes, we can map out how our continents gradually assembled over eons, like a giant slow-motion construction project.
It's mind-blowing. And figuring out past environments. How can we look at rocks and say, this was a desert, or this was a tropical sea?
The rocks tell the story. The types of sediments, the fossils found within them, they're like perfectly preserved time capsules of past depositional environments.
Little snapshots of the past.
Exactly. And then there's sea level. It's not constant, is it?
Not by a long shot.
No. Changes in sea level, rising and falling relative to the land, leave very clear signatures. For instance, you find a layer of marine limestone rock from sea creature shells, sitting right on top of, say, a riverbed conglomerate rock made of pebbles from flowing water. That clearly tells a story of transgression. The sea advanced inland.
Flooding the land.
Right. And conversely, a drop in sea level leads to erosion, breaks in the rock record. We call those unconformities. They're like missing pages in Earth's biography.
Gaps in time. Okay, here's where it gets really interesting for me. Figuring out where the continents were way back when, how do we track that? No ancient GPS?
No, definitely not. But we have some incredibly clever tools. Paleomagnetism is a big one.
Ancient magnetism.
Yeah. As molten rock cools, tiny magnetic minerals inside align with Earth's magnetic field at that specific time. By studying this preserved direction in rocks of different ages from different continents, we can track how the continents themselves must have moved.
That's ingenious.
It is. Then there are marine magnetic anomalies. Think zebra stripes on the ocean floor.
Stripes.
Sort of. Patterns of alternating magnetic polarity locked into the seafloor rocks. They record reversals in Earth's magnetic field over time. The pattern tells us how ocean basins widen between continents.
Wow. And comparing rocks and fossils, too.
Absolutely. If you find the same unique rock formations or identical ancient species on continents now thousands of miles apart, well, it strongly suggests they were once joined, like matching puzzle pieces.
Forensic geology on a planetary scale. And past climates? How do we know if it was tropical at the poles millions of years ago?
Fossils, again, are key. Find fossils of warm-loving organisms in rocks formed at high latitudes. That screams warmer global climate.
Makes sense.
We also analyze isotopes, different forms of the same element in fossil shells and things. The ratios, of different oxygen isotopes act like a natural thermometer. They give clues about past ocean temperatures, even atmospheric conditions.
Amazing. And of course, the big one, the evolution of life itself, the fossil record.
That incredible archive. It shows the progressive changes in life across vast stretches of time. Truly, the biography written in stone we started with.
So with all these detective tools,
Right.
where does this amazing story actually begin?
Well, the story, as we currently understand it, kicks off around 4.57 that's giga annum, billions of years ago.
Billions. Hard to wrap your head around.
It is. It starts with the birth of our solar system, the prevailing theory. Probably a supernova explosion nearby.
A star death triggered our system's birth.
Seems likely. It sent shockwaves and heavier elements into a nearby nebula, a vast cloud of gas and dust. That triggered the nebula's collapse and eventually the ignition of our sun at the center, maybe a few million years later.
So the ingredients were there, and the supernova was the spark.
Essentially, yes. This is chapter 1.
So our sun isn't a first-generation star. It's born from the leftovers of a previous one.
That's wild. Okay, sun shining. What about the stuff that becomes Earth?
In the few million years after the sun lit up, a flattened, rotating disk of gas and dust formed around it, the protoplanetary disk. Like a frisbee of gas and dust.
Kind of. Within this disk, dust and ice particles started sticking together, electrostatically first, then through gravity, gradually forming larger clumps. We see evidence of this early stage in meteorites. They're like leftover building blocks, the earliest planetesimals.
Little planet seeds.
You got it. These planetesimals kept colliding and growing accretion, and within maybe 10 million years, some became protoplanets. Big enough to pull in even more material, like cosmic vacuum cleaners.
A cosmic snowball effect. And these protoplanets weren't uniform balls of rock, were they?
No, not at all. As they got bigger and hotter from collisions and radioactive decay, a key process called differentiation happened.
Sorting themselves out.
Exactly. Denser stuff, mainly iron and nickel, melted and sank to the center, forming a metallic core. This left a surrounding mantle of ultramafic, rock-dense silicate rock rich in iron and magnesium.
So heavy stuff sinks, light stuff floats, even on a planetary scale.
Precisely. By about 4.56 these protoplanets had mostly cleared their orbits. They became true planets. And that date, 4.56 billion years ago, is what geologists generally consider Earth's birth date.
Happy 4.56 billionth. But the early Earth wasn't exactly peaceful, was it?
Far, far from it. Around 4.53 something truly cataclysmic happened. The young Earth collided with a Mars-sized protoplanet. Scientists call it Theia.
Theia. The moon-forming impact.
That's the one. The impact was incredibly energetic. It blasted a huge amount of Earth's mantle and crust into orbit, and some of Theia likely got incorporated into Earth, too. A defining moment.
And that ejected stuff, that became our moon.
Exactly. Coalesced under its own gravity. And the early moon was much, much closer, only about 20,000 kilometers away.
Wow, compared to nearly 400,000 now.
Right. It's still drifting away slowly, a few centimeters a year, but that giant impact left Earth incredibly hot, likely a global magma ocean, hundreds of kilometers deep.
A planet-sized pool of molten rock.
Imagine. Just glowing, flowing lava everywhere, but that intense heat couldn't last forever.
It had to cool down eventually.
It did, relatively rapidly, radiating heat into space. And the initial burst of heat from short-lived radioactive stuff also died down. As the magma ocean cooled, the first solid crust started forming at the surface, like scum on soup.
Not very stable, I imagine.
Probably not. This early crust likely kept sinking back into the molten interior, getting recycled. At the same time, rapid outgassing occurred. Volatiles trapped in mantle minerals escaped via volcanoes, forming a primordial atmosphere.
What was in that early air?
Nasty stuff by our standards. Water vapor, H2O, methane, CH4, ammonia, NH3, hydrogen, N2, carbon dioxide, CO2, sulfur dioxide, SO2. A real toxic mix. Some think comets might have added more volatiles, too.
A primordial greenhouse cocktail. But amid all that fire and toxic air, did liquid water show up early?
The evidence strongly suggests yes, probably by about 4.4 jump. Earth likely cooled enough for a stable solid crust and for liquid water to exist.
How do we know that?
It comes from these incredibly durable zircon grains found in ancient sandstone in Western Australia. Tiny crystals, dating back 4.4 billion years.
Zircons.
They're tough. Extremely. They crystallized from cooling magma, telling us parts of the planet were cool enough for rock to solidify. And crucially, the oxygen isotope ratios within them show signs of alteration by liquid water. Compelling evidence for early oceans, or at least big bodies of water.
So picture this. Small, barren, volcanic lands, pools of acidic water, thick, murky, toxic air.
Not exactly a holiday spot.
Definitely not. And this brings us to the end of the Hadean Eon, right? That first hellish chapter.
Correct. The Hadean, named after Hades for its hellish conditions, gives way around 4.0 GA to the Archean Eon.
Archean, meaning ancient or beginning.
Yep. The transition is sort of marked by the age of the oldest known intact rock on Earth, a gneiss in northwestern Canada, dated to 4.03 billion years. The Archean then spans the next 1.5 billion years, a time of fundamental changes.
Okay, 4.0 billion years ago, start of the Archean. What were the big shifts happening then, moving away from those Hadean extremes?
Well, interestingly, the rock record between about 4.0 and 3.85 GA is really sparse. It's like a page is missing.
Why? What happened?
The likely culprit is the late heavy bombardment. Studies of the moon's craters and other inner planets suggest they, and probably Earth too, got pummeled by meteorites and asteroids between roughly 4.1 and 3.8 billion years ago.
A cosmic shooting gallery.
Pretty much, like the solar system was doing a final chaotic cleanup. This intense bombardment could have effectively resurfaced early Earth, obliterating early crust, maybe even vaporizing oceans and stripping away atmosphere.
Wiping the slate clean, almost.
It's a strong possibility. These massive impacts would have pulverized or melted crust, delivered huge energy, made it hard for stable crust, oceans, and atmosphere to stick around.
And the Earth was still hotter inside, too, right?
Significantly hotter. That higher internal heat meant vigorous mantle convection, more volcanoes, maybe vaster crustal recycling through subduction and remelting, all contributing to why very old rocks are so rare.
So intense destruction, then gradual rebuilding. Yeah. And by around 3.85 Gary, things started to look a bit more geologically familiar, more permanent crust and oceans.
Yes, by then, the crust had cooled and thickened enough for isotopic clocks and rocks to start reliably recording time. Crustal recycling seems to slow down, and importantly, we start finding preserved marine sedimentary rocks.
Ah, evidence of stable water bodies.
Exactly. It indicates that relatively stable land and liquid water existed more or less permanently by this time, a fundamental step away from the initial chaos.
Land and sea. A huge step. What about plate tectonics? Was it operating like today back then, continents moving and colliding?
That's still a hot topic, actually. The Archean Earth was much hotter inside. Some researchers think this led to maybe more rapid mantle convection, more melting, perhaps resulting in many small, fast-moving plates, lots of volcanic arcs, big hotspot volcanoes.
So different rules back then.
Possibly. Others argue the early lithosphere, the rigid outer layer, was too warm and buoyant to subduct effectively, meaning one plate sliding under another was less common.
So maybe not full-blown plate tectonics as we know it.
Maybe not until later in the Archean, but regardless of how exactly the crust was moving, it's clear significant amounts of new continental crust were being generated, building up land masses.
And how did this early continental crust form? Probably not like today's big subduction zones.
One leading model suggests the earliest continents formed by amalgamating smaller, buoyant blocks of crust. These initial bits were likely mostly mephephic igneous rocks like basalt, formed maybe at early convergent boundaries or above mantle plumes and hot spots.
So volcanic islands and plateaus.
Things like that. As these buoyant blocks collided, they got stitched together, forming larger, more stable blocks, less prone to recycling. Then, ongoing activity convergence, rifting, hot spots along the edges and within these blocks added more material.
And it became more continental.
Through partial melting. Pre-existing mafic crust may be deeper down, partially melted. This produces more felsic and intermediate magmas richer in silica, less dense.
Lighter stuff rising again.
Exactly. These lighter magmas rose, solidified in the upper crust or erupted, gradually differentiating the continents into a denser mafic lower crust and a lighter felsic upper crust. Collisions continued, coalescing these into larger protocontinents.
So a gradual buildup, like assembling a jigsaw puzzle over hundreds of millions of years, and eventually these became more permanent.
Precisely. Between about 3.2 and 2.7 GA, this yielded the first long-lived, stable blocks of continental crust, the cratons, the ancient cores of modern continents.
The foundations.
Right. By the end of the Archean, maybe 80% of Earth's present continental area had already formed. Since then, relatively little truly new continental crust from the mantle has been added. Most younger stuff is essentially recycled.
So where do we find this really old Archean crust?
Almost exclusively within these ancient cratons, where they've been sheltered from intense tectonics at plate boundaries. And these Archean cratons typically show 5 main rock types that tell their story.
What are they?
You find nice, heavily metamorphosed rocks from collisions, greenstone metamorphosed oceanic crust bits trapped between blocks, or metamorphosed riftarc basalts, granite from partial melting in arcs or hotspots, graywack sandstone made of rapidly eroded volcanic debris, and chert silica precipitated from deep seawater.
Interesting mix. What about shallow water stuff?
Relatively rare from the Archean, maybe early continents were smaller, flooded more often, or maybe shallower deposits just got eroded away over time.
Okay, so by the end of the Archean, first continents, stable oceans. What about the atmosphere? Still that toxic oxygen-poor mix?
Initially, yes. Similar to the Hadean. But as Earth cooled below boiling and oceans formed, a lot of water vapor condensed out.
Rained out, basically.
Right. And once liquid water existed, huge amounts of atmospheric CO2 dissolved into it, forming carbonic acid, then carbonate minerals and sediments.
Locking up the CO2.
Exactly, pulling it out of the air. So the Archean atmosphere gradually changed from hot, foggy, water vapor and CO2 dominated, to cooler, clearer, dominated by nitrogen. N2.
Why nitrogen?
It's relatively unreactive and doesn't dissolve easily in water, so it just stayed behind as the main component. Rivers flowing over barren land carried dissolved salts from weathering, making the ocean salty, like today.
It's still unbreathable.
Oh, definitely. Likely around 75% nitrogen, 25% CO2, just traces of oxygen, not friendly for us.
Unbreathable air, barren landscapes. Quite the alien Earth. But we can't discuss the Archean without mentioning maybe the most profound development, the beginnings of life.
Absolutely. The Archean isn't just the age of first continents, but very likely the age of first life. Geologists look for 3 main lines of evidence for these earliest whispers.
What are they?
Chemical fossils or biomarkers, durable organic molecules uniquely made by life. Isotopic signatures, specifically the ratio of carbon-12 to carbon-13. Life prefers the lighter carbon-12. And fossil forms preserved physical shapes of cells or structures, though these can be tricky. Inorganic processes can mimic simple shapes sometimes.
So a multi-pronged approach. Chemical, isotopic, physical. What are the key finds?
Isotopic signatures in rocks as old as 3.8 billion years from Greenland hint at biological activity. The oldest undisputed body fossils, likely bacteria and Archaea, are from 3.2 billion-year-old rocks in South Africa and Western Australia, though there are claims for possible fossils as old as 3.5 dare.
And stromatolites, those weird layered rocks.
Ah, yes, stromatolites. Found widely in Archean rocks, especially from 3.5 Gear onwards. They're distinctive layered structures, often dome-shaped.
Built by microbes.
Mostly, yes. Believed to be built by microbial mats, communities of microbes, mainly Archaea or bacteria. They live in layers, trap sediment with sticky secretions. As sediment buries them, they grow upwards towards light or nutrients, creating the layers.
Like little microbial apartment buildings.
Kind of. We even see modern ones forming today in places like Shark Bay, Western Australia. Gives us a window into how the ancient ones formed.
So tangible evidence of ancient ecosystems. And these early microbes, one type in particular, led to a revolutionary change in the atmosphere, didn't they?
Yes, perhaps as early as 3.5 billion years ago, cyanobacteria evolved. Photosynthetic organisms. They harness sunlight, use water and CO2, and crucially, release free oxygen, O2, as waste.
Oxygen, the game changer.
Absolutely pivotal, but initially, very little of that oxygen actually built up in the atmosphere. It was highly reactive. It got quickly consumed by oxidizing iron and other elements in the oceans and on land.
Like the early Earth had a huge oxygen sponge.
Great analogy. It soaked up nearly all the free oxygen produced early on.
But the continuous production eventually overwhelmed the sponge, setting the stage for the next act.
Exactly. The increasing productivity of these photosynthetic organisms eventually exceeded the Earth's capacity to absorb the oxygen. This tipping point led to the gradual accumulation of free oxygen in the atmosphere, a massive transition. And this brings us to the next major eon, the Proterozoic.
The Proterozoic Eon, meaning earlier life, a truly immense period, stretches for, what, 2 billion years?
Yeah.
From 2.5 billion down to 541 million years ago.
That's right. Nearly half of Earth's entire history packed into one eon.
Incredible. And it's characterized by a big shift, right? From those small, fast plates and oxygen-free air to larger, slower plates and an oxygenated atmosphere.
Yes, it's a period of profound transition on multiple fronts. 2 billion years is just staggering to comprehend.
So what were the key changes with the continents during this vast time? Did those Archean cratons start coming together?
New continental crust kept forming, but definitely at a slower rate than in the Archean. By the middle Proterozoic, maybe over 90% of Earth's current continental crust was already formed.
So the focus shifted from making crust to rearranging it.
Exactly. The big story is the gradual assembly of those earlier Archean blocks, plus various volcanic arcs and hotspot bits, through collisions and accretion, suturing themselves together like a tectonic quilt, forming larger land masses.
So continental growth slowed, but continents got bigger and more organized. Did the size matter?
Absolutely. Size really matters for continents. The interiors of large land masses get isolated from the intense heat and activity at the margins.
Ah, so they cool down and stabilize.
Precisely. This allows the interiors to cool, strengthen, become more stable. These large, cold, stable regions are the cratons we talked about. Their foundations were laid in the Archean, but they really became fully assembled and stabilized during the Proterozoic. By about 1 billion years ago, all the major cratons that form the cores of modern continents were essentially in place.
Like the Canadian Shield, the Siberian Platform. Those ancient hearts were formed by then. How are they structured, if you cut through one?
You'd see two main parts, the shield and the cratonic platform. In shield areas, like the Canadian Shield, the ancient Precambrian basement rock, older than 1 Ga, is exposed right at the surface, often eroded into low-relief landscapes.
Okay. And the platform.
Surrounding the shield, often extending under areas like the Great Plains, is the platform. The ancient basement is still there, but it's covered by a relatively thin blanket of younger sedimentary rocks, mostly Paleozoic and Mesozoic, deposited when shallow seas covered these stable interiors.
And geologists divide these basements further.
Yeah, into geologic provinces based on age, rock types, history. Like in the U.S. Southwest, the Yavapai and Mazatzal provinces represent distinct episodes of accretion, maybe 1.8 to 1.6 billion years ago, when arcs and fragments collided with the older core.
So our continents are complex mosaics. Ancient cores, younger bits tacked on, younger sediments on top. And this assembly eventually led to supercontinents.
Exactly. Over the Proterozoic, these collisions eventually resulted in one or more supercontinents land masses with most or all of Earth's continental crust. The most well understood is Rodinia.
Rodinia, when did that form?
Believed to have assembled by around 1 billion years ago, involved major collisions like the Grenville orogeny massive mountain building, maybe Himalayan scale. Reconstructions show how pieces that became modern continents fit together.
Did Rodinia last?
Evidence suggests it started breaking apart later, maybe 800 to 600 million years ago. There's also talk of another, maybe shorter-lived supercontinent, Pannotia, around 570 Ma, possibly a reassembly of some Rodinia fragments.
That's supercontinents forming, breaking apart, a slow cosmic dance. But the Proterozoic wasn't just about continents, was it? Life also changed profoundly.
Absolutely. At the start, life was mostly prokaryotic simple single cells like bacteria, archaea, no nucleus. But the Proterozoic saw the crucial transition to eukaryotic life.
Our kind of cells, with a nucleus and organelles.
Right. Complex cells, chemical fossils hint eukaryotes might go back to 2.7 Ga, but the first accepted body fossils appear around 1.9 Ga, becoming more common after 1.5 Ga.
A huge step up in complexity.
Fundamental. It provided the toolkit for multicellular life plants, animals. The later Proterozoic, after about 800 Ma, saw a remarkable increase in complexity. Ciliate protozoans appear around 750 Ma.
And then the Ediacaran fauna.
Yes. By perhaps 620 Ma, certainly by 565 Ma, we find the Ediacaran fauna, the first widespread evidence of large multicellular animals. Some might have even had simple organs.
What did they look like?
Enigmatic things. Named after finds in South Australia, some resembled jellyfish, others worms, some segmented. Others were just weird bag-like or quilt-like shapes. An intriguing early experiment in complex life.
So simple cells to complex cells to these bizarre multicellular creatures. Huge leaps. And all this time, the atmosphere was changing dramatically too. The Great Oxygenation Event.
Yes, the Great Oxygenation Event, GOE, a period of dramatic, sustained increase in atmospheric oxygen, O2.
When did this happen?
Roughly between 2.4 and 1.8 billion years ago. Photosynthesis had been around, but this is when oxygen production by cyanobacteria really started to consistently overwhelm the planet's ability to absorb it. Free oxygen began accumulating significantly for the first time.
How do we know? What's the evidence?
Several key lines, one big one. Widespread banded iron formations, BIFs.
Those stripy iron rocks.
Yeah, distinctive layers of iron oxide minerals like hematite, magnetite, alternating with silica-rich chert. They likely precipitated from iron-rich oceans.
How does oxygen fit in?
In low oxygen water, iron stays dissolved as ferrous iron, Fe2+. As oxygen levels rose, it reacted with the dissolved iron, forming insoluble ferric iron Fe3+ oxides, which then rained down onto the seafloor, creating these layers.
And most BIFs formed during that 2.4 to 1.8 Joule window.
The vast majority. It's a primary source of iron ore today. Indicates widespread ocean oxidation then. Another clue, the disappearance of easily oxidized minerals like detrital pyrite, iron sulfide, and uraninite in sandstones younger than about 2.4 John. Their presence in older rocks suggests low oxygen.
And red beds.
Right. Red beds, rusty red sedimentary rocks, due to iron oxide coatings, appear after about 1.8 Gres. Shows groundwater and surface environments were becoming oxygen-rich.
So oxygen levels shot up.
They rose significantly, maybe to around 3% of modern levels by 1.8 Gres, then stayed relatively stable until about 600 million years ago, before rising again towards the end of the Proterozoic.
And this oxygen had huge consequences for life.
Profound, paved the way for efficient aerobic respiration, eventually led to the ozone layer, shielding the surface from UV, making land more habitable.
Oxygenating the planet fundamental, but the Proterozoic had one more dramatic twist, right? Snowball Earth?
Yes, the late Proterozoic saw compelling evidence for multiple periods of globally extensive glaciation, so extreme they led to the snowball Earth hypothesis.
When were these?
Most documented are the Sturtian glaciation around 720-660 May, and the Marinoan glaciation around 650-635 May.
What's so striking about them?
We find glacial evidence like tellites, striate bedrock in rocks interpreted to have been near the equator back then, based on paleomagnetism. Ice at the equator.
Exactly. That seeming contradiction led to the radical idea that maybe the entire Earth's surface, oceans included, was covered in a thick layer of ice. A giant snowball in space.
A completely frozen Earth. Unimaginable. How could anything survive?
Extremely challenging. Life would likely be restricted to refugia, maybe near deep-sea hydrothermal vents where geothermal heat kept water liquid supporting chemosynthesis, or maybe land-based hot springs, volcanic areas providing localized meltwater.
How did it melt, if the whole planet was reflective ice?
The thinking is continued volcanic CO2 buildup. Ice cover drastically reduced rock weathering, which removes CO2, and stopped CO2 dissolving in frozen oceans, but volcanoes kept pumping it out.
So CO2 built up in the atmosphere.
Over millions of years, CO2 is a greenhouse gas. Eventually, it trapped enough heat to start melting the ice, maybe near the equator first. Once melting started, the darker water or land absorbs more heat than ice, leading to a runaway warming effect, rapidly thawing the planet.
Wow. And maybe these extreme freeze-thaw cycles spurred evolution.
It's an interesting idea. The stress and rapid environmental changes afterwards might have driven innovations, maybe helping set the stage for the Ediacaran fauna.
So extreme freezing, then dramatic thawing, driven by Earth's own processes. The end of the Proterozoic must have been a time of huge upheaval, setting the stage for the Phanerozoic.
Absolutely. As the Proterozoic closed around 541 million years ago, the climate was generally warming, supercontinents were breaking up and reforming, life was diversifying, and a key development, the first organisms with mineralized shells and skeletons.
Hard parts. That makes fossils easier to find, right?
Much easier. This biomineralization led to a far richer, more complete fossil record compared to the Precambrian. This more detailed record marks the start of the Phanerozoic Eon, the current eon, the age of visible life.
Visible life sounds like the story really kicks into high gear now. And the Phanerozoic is split into 3 eras: Paleozoic, Mesozoic, Cenozoic.
Correct. The last 541 million years. Paleozoic means ancient life, 541-252 Ma. Mesozoic is middle life, 250-66 Ma. And Cenozoic is recent life, 66 Ma to present.
Okay, let's start with the Paleozoic. What did the world look like then? Geography, climate.
Beginning of the Paleozoic, the supercontinent Pannotia had broken up. We had smaller continents like Laurentia, roughly North America, Greenland, Gondwana, South America, Africa, Antarctica, India, Australia, Baltica, and Europe, and Siberia drifting apart.
Creating new oceans between them.
Yes, and along the edges of these continents where crust-stretched passive margins, broad passive margin basins formed, collecting thick piles of sediment eroded from land.
And sea levels were fluctuating.
Significantly throughout the Paleozoic. Repeated transgressions, shallow epicontinental seas, flooding continental interiors, and regressions sea level dropping, causing erosion, creating
Like
unconformities.
in the Grand Canyon, that layer cake look.
Exactly. The Grand Canyon beautifully exposes hundreds of millions of years of this Paleozoic layer cake stratigraphy. You can literally walk through time.
So early Paleozoic,
Hmm.
continents breaking up, shallow seas flooding in, and a huge explosion of life in the oceans. The Cambrian explosion.
Oh, precisely. Shortly after the Cambrian began, 541 Ma, life in the oceans underwent this remarkable, relatively rapid diversification, the Cambrian explosion.
What kind of life appeared?
Over just a few tens of millions of years, most major animal phyla, the fundamental body plans, appeared. First, animals with hard shells, exoskeletons like the iconic trilobites, also mollusks, brachiopods, early nautiloids, gastropods, graptolites, echinoderms.
Why then? What triggered it?
Still debated, but the breakup of supercontinents likely played a role creating new, isolated marine environments, driving evolution. Complex food webs developed. First reefs built by sponges with mineral skeletons appeared. It's a pivotal moment, setting the blueprint for animal life.
And this continued into the next period, the Ordovician.
Yes, momentum continued. New organisms like crinoids, sea lilies, and significantly the fur vertebrate animals, jawless fish.
Jawless fish, first creatures with a backbone. Another milestone. But land was still pretty empty.
For most of the early Paleozoic, yeah. Land was stark, bare rock, sediment, no real soil. Plus, the ozone layer was likely thinner, high UV radiation, very hostile.
When did plants first try land?
Earliest hints are late Ordovician, small plants, probably right near water. So life flourished in the sea, but land remained largely barren. The end of the Ordovician also saw a major mass extinction, possibly linked to a brief ice age and sea level drop.
Okay, so life booming in the sea, land still waiting. What changed in the Middle Paleozoic Silurian and Devonian periods? Continents moving back together, more life on land.
Middle Paleozoic saw general warming greenhouse conditions, sea level rose again, flooding continents, big reef complexes grew in warm, shallow seas, built now by corals more like today's.
And tectonics, mountains building.
Active period. Continents started converging again. The Caledonian orogeny hit eastern Greenland, Scandinavia, Scotland, as Laurentia and Baltica collided. Later, the Acadian orogeny built mountains in the Appalachians as Laurentia hit smaller blocks, then Gondwana.
What about Western North America?
Remained a passive margin until the late Devonian antler orogeny. First, big collision out west, with an island arc. These orogenies shed huge amounts of sediment, forming deposits like the red beds in the Catskills, eroded from the Acadian highlands.
Mountains rising, eroding, shaping the landscape, and life finally made a big push onto land.
Absolutely. Silurian and Devonian saw a major land colonization. Evolution of complex vascular plants, woody stems for support, veins for transport, allowed them to grow bigger, move away from water. By late Devonian, swampy forests of tree-sized relatives of club mosses and ferns were widespread.
And animals followed.
Concurrently, yes. Terrestrial animals appeared and diversified. Arthropods, spiders, scorpions, early wingless insects, crustaceans colonized land and fresh water. In the oceans, jawed fish, including early sharks and bony fish, diversified hugely.
And amphibians, the first steps onto land.
Right at the end of the Devonian, the first tetrapods, four-legged vertebrates, like the famous Tiktaalik, made initial forays onto land, breathing air with lungs, fins adapted for support in shallow water and on land.
Tiktaalik, that fish-amphibian transition. Pivotal. What about the late Paleozoic? Carboniferous and Permian, time of climate change and a supercontinent forming.
Yes, late Paleozoic saw significant climate shifts. Carboniferous cooled overall icehouse conditions, especially in the south, where Gondwana drifted over the South Pole, getting glaciated.
But equatorial regions were different.
Very different. Laurentia and other northern continents near the equator had warm, humid conditions, fostered vast, swampy forests, giant lycophytes, seed ferns.
The coal swamps.
Exactly. Incomplete decay of all that plant matter formed many of the world's major coal deposits, hence Carboniferous coal-bearing. Moving into the Permian, the southern cooling continued, ice sheets expanded on Gondwana and Siberia, but the overall global climate became somewhat drier in many areas.
A world of contrasts, ice caps and coal swamps, and this was when Pangaea assembled.
Correct. Intense continental convergence. The biggest event. Gondwana collided with Laurentia and Baltica. This caused the Alleghanian orogeny in North America, the final phase of Appalachian mountain building.
Who hit whom?
Eastern North America hit northwestern Africa. The Gulf Coast hit northern South America, created a vast, complex mountain belt across the heart of what became Pangaea. The eroded remnants are today's Appalachians and Ouachitas.
So by the end, almost all land was one giant supercontinent.
Pretty much. Pangaea surrounded by the global ocean panthalassa.
Pangaea. Imagine walking from North America to Antarctica.
Yeah.
These collisions must have had other effects too, like the Appalachian Fold Thrust Belt and the ancestral Rockies.
Yes. The huge compression of the Alleghenian orogeny caused widespread thin-skin deformation west of the main mountains, the Appalachian Fold Thrust Belt. Sheets of sedimentary rock detached from basement got pushed west along thrust faults, creating folds. That's the ridge and valley topography.
In the ancestral Rockies, far inland.
The stresses reached deep into the continent, reactivating ancient faults in the basement. Caused basement uplifts, big blocks of Precambrian rock pushed up, forming ranges like the ancestral Rockies in present-day Colorado, Utah. Erosion of these filled adjacent basins.
And Pangaea formation involved other collisions too.
Oh yeah, Africa hit southern Europe, Hercynian-Variscan orogeny. An ocean closed in Russia, uplifting the Urals. Bits of China and Asia attached to Siberia, a truly global assembly.
So late Paleozoic, dynamic tectonics, continents crashing, Pangaea forms, mountains rise everywhere. What about life during all this change?
Life continued evolving, becoming more modern-like. Carboniferous coal swamps had diverse insects, giant dragonflies, then insects with foldable wings like early cockroaches.
Wow.
Big innovation.
And plants.
As climate dried in the Permian, gymnosperms became dominant early conifers, cycads, better adapted than the swamp plants. Among vertebrates, amphibians thrived, but the Permian saw a big diversification of reptiles.
Because of the amniotic egg.
Key adaptation. The shelled egg allowed reptiles to reproduce entirely on land, freeing them from water unlike amphibians, allowed them to colonize wider habitats.
Reptiles taking over the land. But the Paleozoic didn't end quietly, did it? The Permian-Triassic extinction, the Great Dying.
No, it ended catastrophically. Around 252 million years ago, the most severe mass extinction ever. Worse than the dinosaur one later. Estimated over 95% of marine species, maybe 70% of land vertebrates, disappeared.
What caused it?
Still debated.
Intense research ongoing, leading hypothesis, extraordinary prolonged volcanic activity in the Siberian traps, massive basalt lava flows.
Releasing what?
Enormous amounts of greenhouse gases, CO2, methane, toxic stuff, sulfur dioxide, chlorine, could have caused runaway global warming, ocean acidification, widespread ocean anoxia, lack of oxygen, massive ecosystem collapse.
Any other ideas? Meteorite impact.
That's been proposed, but definitive evidence for a major impact right at the boundary is still debated. It was likely a combination of factors, but whatever the cause, it fundamentally reshaped life, clearing the stage for the Mesozoic Era. The Permian extinction, the Great Dying, truly devastating. And from that, the Mesozoic Era rose middle life, the age of dinosaurs, Triassic, Jurassic, Cretaceous periods, 252 to 66 million years ago. The world must have been very different after that extinction.
Indeed. Early Triassic was relatively barren, hostile. Pangaea was still mostly intact, though rifting started late in the Triassic, beginning its breakup.
When did the breakup really get going?
By the end of the Jurassic, it was well underway. The mid-Atlantic ridge started forming as North America rifted from Europe and Africa, initial opening of the North Atlantic and Gulf of Mexico.
What was that early Atlantic like?
Narrow, shallow. High evaporation in these restricted basins led to thick evaporate deposits, salt layers along the margins, now deeply buried, especially under the U.S. Gulf Coast. Important for geology and oil gas there.
So Pangaea is still there, but starting to crack. What was the climate like?
Generally warm, relatively equable globally through the Triassic and Jurassic. No big polar ice caps like today. Vast interior of Pangaea was likely arid or semi-arid.
Any evidence of that?
Yeah, in North America's interior, extensive non-marine environments, big rivers, basins. Think of the stunning red sandstones in Zion National Park, those cross-bedded layers. Preserved sand dunes from a huge early Jurassic desert.
Wow. Did seas come back inland?
Sea level started rising middle Jurassic, submerging parts of the future Rockies. Shallow seas encroached.
And while the east was pulling apart, the west coast of North America was getting very active. Subduction and accretion.
Yes, a long, complex history of convergent boundary tectonics all through the Mesozoic. Starting late Permian, oceanic plates subducted under western North America, generating volcanic island arcs offshore.
And these collided with the continent.
Periodically, yes. These arcs, plus oceanic plateaus from hot spots, slammed into North America and got accreted, added as exotic terrains. Crustal fragments with different histories significantly expanded western North America.
When did the main Pacific plate start subducting?
By the end of the Jurassic, subduction of the Pacific Ocean floor directly beneath North America was established, created a major continental volcanic arc, the Sierran Arc, hundreds of miles long, active all through the Cretaceous, like the modern Andes.
So east side rifting, west side growing via collisions and volcanoes, and life was recovering from the Permian extinction.
Gradually, yes. Early Mesozoic saw rediversification. New reptiles filled empty niches. Oceans saw large marine reptiles like plesiosaurs, ichthyosaurs. New corals became reef builders.
And on land.
Gymnosperms diversified. First turtles appeared, flying reptiles, pterosaurs, and crucially, the first true dinosaurs evolved late in the Triassic.
What made them different?
Legs positioned directly under their bodies, more efficient movement, maybe higher metabolism, possibly warm-blooded.
They took off of the Jurassic.
Big time. By the end of the Jurassic, dinosaurs dominated. Gigantic sauropods, long necks, armored stegosaurs, and the first feathered birds like Archaeopteryx, mix of reptile and bird features.
What about mammals?
Earliest ancestors appeared late Triassic. Small, furry, mostly rat-like, remained minor players in a dinosaur-dominated world for a long time.
Dinosaurs finally taking center stage. What about the late Mesozoic, the Cretaceous, final period of the age of reptiles, defining events?
Cretaceous saw Pangaea's breakup continue. South America, Africa split from Antarctic Australia. India started its fast northward journey towards Asia.
And sea levels.
Rose globally to their highest point in 200 million years. Flooded vast continental areas, creating huge, shallow epicontinental seas, like the Western Interior Seaways splitting North America, Gulf to Arctic.
Wow. Climate still warm.
Yes, persistent greenhouse climate.
Yes.
On the West Coast, subduction and accretion continued, more exotic terrains added. The Sierran Arc stayed highly active, pumping out magma like the modern Andes.
Where is that arc now?
Its eroded roots form the granite batholiths of the Sierra Nevada in California. West of it, scraped-off sediments formed a massive accretionary prism today's coast ranges of California.
So North America split by a sea, west coast of volcanic mess, and then the Laramide orogeny, building the Rockies. How did that fit in?
Around 80 million years ago, late Cretaceous into early Cenozoic, the style of deformation changed in the U.S. West. A new style began, the Laramide orogeny.
Different from earlier mountain building.
Yes. Instead of thin-skinned thrusting, shallow layers sliding, the Laramide involved thick-skinned reverse faults. These went much deeper into Precambrian basement rocks.
Pushing up big blocks of ancient rock.
Exactly. This eastward sweep of deformation caused broad uplifts of basement blocks, forming the major ranges of the U.S. Rockies. Overlying sediments often bent into large monoclines.
Why the change?
Still debated. Maybe a shallower angle of subduction of the Pacific plate, perhaps due to a buoyant oceanic plateau hitting the trench or change in convergence rate, affecting deformation further inland. Interestingly, this didn't happen in Canada. The Canadian Rockies kept growing via thin-skinned thrusting.
Different styles side by side. And the super high sea levels, what drove that?
Likely a combo. Higher rates of seafloor spreading meant more young, hot, buoyant oceanic crust displacing seawater. Plus, formation of large oceanic plateaus, huge volcanic outpourings from mantle plumes also displaced water.
And climate feedback?
More volcanism, spreading ridges, plateaus, released lots of CO2. Greenhouse effect warmed the planet, causing thermal expansion of seawater. Warm water takes more volume, maybe melted any polar ice, all adding to sea level rise.
A confluence of factors creating a flooded greenhouse world. And life. Dinosaurs peaking.
Absolutely. Modern bony fish groups appeared, dominated oceans, huge swimming reptiles, mosasaurs, plesiosaurs got enormous, giant sea turtles too.
Bad land plants.
Cycads declined, angiosperms, flowering plants, including hardwoods, grasses exploded in diversity, becoming dominant, outcompeting conifers.
And the dinosaurs.
Reached their zenith. Ecological diversity occupied almost every niche, small predators, giant herbivores. Social herds became common, preyed on by things like Tyrannosaurus rex.
T-Rex, iconic. What about flyers and mammals?
Pterosaurs continued, birds diversified into more modern forms. Mammals, still mostly small but diversified lineage-wise, developed bigger brains, specialized teeth, hinting at their future.
A vibrant world. But it all ended suddenly, didn't it? The KPG boundary event.
Yes, Cretaceous and the whole Mesozoic era ended abruptly 66 million years ago. The Cretaceous-Paleogene KPG extinction, another Big Five event.
How bad was it?
Wiped out maybe 76% of all species. All non-avian dinosaurs gone, birds survived. 90% of plankton, up to 75% of plants. Devastating.
And the cause, the asteroid impact.
That's the overwhelming scientific consensus now. impact of a large asteroid or comet, 10, 15 kilometers wide, hitting in the Yucatan Peninsula, Mexico, created the Chicxulub crater.
The evidence is strong for that.
Remarkably strong. A thin global clay layer at the boundary, the KPG layer, contains super high iridium levels rare on Earth, common in meteorites.
What else is in that layer?
Microscopic glass spheres, tektites, or spherules. Molten rock ejected by impact, solidified falling back. Shocked quartz grains with structures from intense impact pressure. Soot and ash from massive wildfires ignited by the impact heat. And the Chicxulub crater itself, buried now, is the right size and age.
What were the immediate effects?
Catastrophic. Massive earthquakes, unimaginable tsunamis, huge amounts of dust, ash, sulfate aerosols thrown into the upper atmosphere.
Blocking sunlight.
Exactly. Creating a dense global haze, maybe for months or years. Shutting down photosynthesis, collapsing food webs on land and sea, a prolonged impact winter.
And acid rain.
Vaporizing sulfur-rich rocks at impact released massive sulfur dioxide, led to widespread acid rain, ocean acidification, stressing marine life further. The combination darkness, cooling, then maybe warming, acid rain, ocean acidification created an environmental crisis leading to the mass extinction.
A world-altering cosmic blow. End of the Mesozoic, clearing the stage for the Cenozoic.
The Cenozoic Era, recent life, or age of mammals, began 66 million years ago, continues today, divided into Paleogene, Neogene, Quaternary periods. Quaternary includes Pleistocene and Holocene epochs.
What's the big story of the Cenozoic?
Continued plate tectonics shaping modern continents and oceans, and the remarkable diversification and success of mammals, filling niches left by the dinosaurs.
So the world after dinosaurs, what major continental shifts led to today's map?
Final breakup of Pangaea's southern bits. Continents drifting to present positions. Australia split from Antarctica, moved north. Greenland drifted from North America. North Sea formed. Atlantic kept widening. Americas moved west.
And the Gondwana continents moving north caused collisions.
Big time. India's ongoing collision with Eurasia, starting around 40 Ma, uplifting the Himalayas and Tibetan Plateau. Africa collided with Eurasia, forming the Alps, Caucasus, Zagros. Australia hit New Guinea, building mountains there.
Creating the Alpine Himalayan chain?
Yes, the cumulative effect. The largest active continental orogenic system today, stretching across Eurasia.
So, today's major mountains are relatively young geologically. What about the Western Americas? Still active?
Yes, convergent boundaries continued much of the Cenozoic South America. Nazca Plate subducting under South American Plate, uplifting the Andes. North America, Farallon Plate subducted until about 40 Ma, end of Laramide.
Then things changed.
Big change around 25 Ma. The spreading ridge between the Farallon and Pacific plates hit the North American margin, transformed much of the boundary from subduction to a transformed fault.
The San Andreas Fault.
Exactly. Pacific plate started sliding horizontally past North American plate, created the San Andreas system in California. Queen Charlotte Fault off Canada. Pacific moves north 6 summer year relative to North America now.
Where is subduction still happening?
Active convergence now mainly at the ends. Pacific Northwest, Washington, Oregon, and California. Juan de Fuca Plate, Farallon remnant subducts, feeding Cascade volcanoes, and further south along the Middle America Trench.
So the San Andreas is relatively recent, marks a major shift. What about the Basin and Range province, that weird landscape in the U.S. West?
Ah, the Basin and Range. Vast area, alternating north-south mountain ranges and sediment-filled valleys. A major Cenozoic feature.
How did it form?
Related to the end of compression after the Laramide. Starting around 20 Ma, the region began experiencing significant east-west extensional tectonics. Crust pulled apart.
Stretching the crust.
Yes. Thinned and fractured along numerous normal faults. Blocks dropped down relative to others. Uplifted blocks formed the ranges. Down-dropped blocks formed the basins, filling with eroded sediment. The province has stretched maybe to twice its original width over 20 million years.
And Yellowstone fits in how?
The northern end of the Basin and Range is cut off by the Snake River Plain, the track of the Yellowstone hotspot. It's migrated northeast as the plate moved over it, leaving a trail of volcanic calderas.
Mountains pulled apart, hotspot track, geologically dynamic. What about Cenozoic climate? Post-dinosaurs, age of mammals, trends.
Significant long-term change. Early Cenozoic, especially Eocene, was generally warm globally. Subtropical conditions far north-south.
Then it cooled.
Starting early Oligocene, around 34 Ma, A long cooling trend began. Significant ice sheets reestablished on Antarctica, shift to icehouse conditions. Cooling continued through Miocene, grasslands expanded.
What about Panama?
Pliocene, around 3 Ma, Isthmus of Panama finally closed, connecting North and South America. Dramatically altered ocean currents, possibly contributed to northern hemisphere cooling, Arctic sea ice development.
Leading to the Ice Age?
The Quaternary period, starting 2.6 Ma, is defined by the Pleistocene Ice Age, series of at least 20 major glacial expansions and retreats across northern continents, driven by Milankovitch cycles' orbital variation.
What happened during glacials?
Massive ice sheets grew, advanced south, lowered global sea level significantly 100 meters or more, exposed continental shelves, created land bridges like Bering Strait, glaciers carved landscapes, deposited sediment, created lakes.
And interglacials?
Warmer periods, glaciers retreated, sea level rose, submerged land bridges. We're currently in an interglacial. The Holocene epoch started about 12,000 years ago.
So, Cenozoic. Long cooling, punctuated by dramatic Ice Age cycles. And against this backdrop, mammals rose to prominence.
Yes, the KPG extinction opened up ecological niches. Mammals were major beneficiaries. Early Cenozoic plant life recovered angiosperm, gymnosperm forests. Grasses spread across plains. Mammals underwent rapid adaptive radiation,
Filling dinosaur roles?
diversifying into wide array of forms, sizes, filling many ecological roles. Most modern mammal groups originated early Cenozoic, hence Age of Mammal.
And the megafauna? Mammoth.
Later Cenozoic saw evolution of very large mammals, mammoths, mastodons, giant sloths, giant beavers, giant bears. Many went extinct, late Pleistocene, early Holocene, last 10–50,000 years. Human hunting possibly played a role.
The age of mammals, leading eventually to us. Incredible arc.
Indeed. Ape-like primates diversified Miocene, 23 Ma. First human-like primates, hominins, in Africa. 4 Ma, genus Homo, 2.4 Ma. Homo erectus, upright stone axes, 1.8 Ma. First to migrate out of Africa.
And Homo sapiens.
Our species diverged from Neanderthals, Denisovans, 500K. Anatomically modern Homo sapiens evolved Africa, 200K. Spread globally, coexisted with Neanderthals, Denisovans until they went extinct, 25K, leaving only us.
So geologically recently, humans became a dominant force, leading to talk of the Anthropocene.
The Anthropocene, an informal but widely used term for a proposed new epoch, where human activities are the dominant global influence on ecosystems, geology.
When did it start? Still debated.
Ongoing debate. Proposals range from early agriculture thousands of years ago to the Industrial Revolution, or even the mid-20th century Great Acceleration. Regardless of timing, it highlights our profound growing impact, leaving a distinct geological signature.
From a chaotic magma ocean to continents, early life, the rise and fall of oxygen, supercontinents assembling, breaking, the long reign of dinosaurs, their sudden end, ice age swings, and finally humanity's recent rapid global impact. It's an absolutely breathtaking story, billions of years.
It truly is. And as we've seen, Earth's history is this constant interplay between geology, tectonics, volcanoes, erosion, and biological evolution, each profoundly influencing the other over vast timescales. Understanding this deep history gives crucial perspective on our planet's dynamic nature.
So as we reflect on this immense journey through Earth's biography, here's a final thought for you listening. Considering the profound, often rapid changes our planet has seen, what major lasting marks do you think the Anthropocene, this human-dominated time, will leave in the geological record millions of years from now?
That's a very thought-provoking question. Future geologists, they'll undoubtedly find a distinct layer. Evidence of rapid climate change, altered isotopes, different sediments, widespread extinction evidence, lots of biodiversity, maybe preserved nanomaterials like plastics.
Our constructions too. Cities, mining.
Likely. Large-scale landscape modification from agriculture, urbanization, mining will leave a clear signature. Widespread concrete, other artificial materials. It's a sobering thought, considering our legacy and the long history of this evolving planet.
Definitely something profound to consider. If you, the listener, want to explore any specific events, times, or concepts we've touched on, we'll really encourage you to dive deeper. There's a whole universe of discoveries out there.
And just to confirm, this deep dive has aimed to cover the major topics in a comprehensive way, like you'd find in an introductory chapter on Earth's history, such as in Earth. Portrait of a planet. We've hit core geological concepts, deep time, tectonics, the rock cycle implicitly, key processes. We've used examples relating to real places often featured as Geotours Grand Canyon, Appalachians, Basin and Range, Zion, Himalayas, and hopefully you've got a sense of how geologists piece this all together, analyzing rocks, fossils, other evidence. That's the hands-on application, understanding the past to better grasp the present and future. We journeyed from Earth's formation through the eons and eras, hitting major events, life's evolution, and the interconnectedness of it all.